All right, let's talk about what we call the modulus of a complex number. Up here at the top, we've defined the length of the complex number segment is called the modulus of the complex number. So length, what are we talking about? This relates back to kind of what we saw as on our vector graphs. So this says graph the complex number of 3 minus 5i. So remember, we move 3 in the real direction, negative 5 in the imaginary. So here's our real number axes. Here's our imaginary number axes. So we're going to go imaginary number 1, 2, 3 in the positive, down 1, 2, 3, 4, and 5. So here's that complex number. And it says connect the graph point to the origin with a line segment. So kind of like the vectors there, we're going to connect it to the origin. If this is the case and we wanted to find the modulus, this is what we call the modulus of a complex number. It's the length from the origin out to the complex number on the graph. And the modulus, again, is length. So if you think about all the things you've learned about in finding lengths on graphs, we can do this in a couple of ways. One, we can use the distance formula. This is the point 0, 0. This is, right, the point 3, negative 5. So if I wanted to, I could use the distance formula. And some of you are very comfortable with using the distance formula. Let me just remind you what it is. We take the x value, right, of one point, subtract the x value of the other, and square it. So we're finding the difference in the horizontal direction. And we do the y value minus the y value in the vertical direction. That's just great. We can use that every single time. However, what I want you to realize is that one of those points is always 0, 0. So if this is 0 and this is 0 every single time, then really you just need the one value, right, squared, and the one value squared. So we could write this as x2 squared plus y2 squared. We don't need the other part. This is really the formula for the modulus. If I was writing a complex number and I wanted to calculate its distance from the origin. So we can use that. You can also think about it as the Pythagorean theorem if you would like to. So some of you that are really good at triangles, right, we have like this goes over 3, this goes down 5. So the distances here is 3 squared plus 5 squared creates a right triangle. So that should equal the length, or the modulus squared. Now essentially this is actually the same thing. If I'm saying the modulus squared is equal to the square root of 3 squared, right, plus 5 squared. Oh, that's terrible. M squared equals 3 squared plus 5 squared. Sorry about that. Then when I square root this side to solve, it's essentially exactly what this formula is. So all of those are really the same thing. But our modulus here, and let me kind of write this, absolute value bars are represented to are used to represent modulus because these represent distance, right, from the origin. So if these are absolute value bars and I have x plus yi, a complex number, then again I would write my modulus as whatever that x value is squared plus the y squared, and that would allow me to calculate that modulus. And we're going to leave it in exact radical form unless you're asked to round it. So if you can, you will simplify your radicals. So let's do this on a couple of these. Number 3, again, we see these bars, and it's asking us here in these instructions to determine the modulus of each of the complex numbers. And again, when you see those bars, it automatically means length, or the square root, right, using that formula. So here we go. We are going to do the square root of, we get 21 squared, and then plus negative 3 squared. Right, these are distances, so I guess if you didn't plug in negative 3, that would not be a big deal. You could use positive 3. And then we go ahead and we calculate. So 221 squared is 441 plus 3 squared, or negative 3 squared, which is 9. That's equal to the square root of, if we add that together, we get 450. Now again, if we can, we'll go ahead and simplify this. So this looks like we could do 9 and 50. You can break this down however you would like to. There's a group there, 25 and 2, 5 and 5. There's another group. So it looks like we've got 3 times 5 to pull out front, and on the inside we just have a 2 left. This would represent the modulus, or the length of that complex number, or its distance from the origin. Number 4, 1 plus 8i, finding its modulus. So again, we do the same thing. We set up the square root, and we do the first component squared, or the horizontal distance, plus the vertical distance squared, so 8 squared, and then we simplify. So 1 squared is 1, 8 squared is 64, so this ends up being the square root of 65. Okay? And I don't believe that simplifies, so we would just leave that as the square root of 65. Okay, that is the modulus of a complex number. Now, putting this all together, if we're using this notation here, it says given that z sub 1 is equal to this complex number, and z sub 2 is this complex number, and z sub 3, and so on, determine the following. So immediately when we see those absolute value bars, we know that this means the modulus of z2. So the modulus of z2, I'm going to put z2 in there, right? When I start to create my equation, notice there is no real component. So I guess I could put 0 squared and negative 6 squared just to use that formula correctly. But essentially, right, we're saying this is 0 plus 36. So the square root of 36 is equal to 6. So the modulus, or the length of this complex number, would be 6. Now that makes sense, because if you think about the graph that we practiced on, right, here's our real and here's our imaginary. If this is just at -6, it doesn't move left or right at all. That means it went down 6. So it's sitting right here. So that makes sense that it's 6 units away from that origin. All right, the next one says z1 plus z3, and we're finding the modulus. So I'm going to write modulus. I'm going to put z1 in here, so we're going to put 7 plus 2i plus z3, which in this case is 1 minus 4i. And here's our modulus there. So this is going to be equal to, if I add the like terms, I get 7 plus 1, which is 8. 2i minus 4i is negative 2i. So when we calculate this modulus, we have 8 as one component, negative 2 as the other component. So we end up with 64 plus 4 here is equal to the square root of 68. Now this one we probably can break down, so we would if we could. We got 2 and 34, 2 and 17. That gives us a group of 2's. So we would finish with 2 square root of 17. You can always approximate these two just by plugging them into a calculator. Lastly, let's talk about how this could apply to a simple application. Now, there are much more complicated applications we could look at, but this just kind of allows you to relate it a little bit to a directional graph, and specifically to represent speed. So notice here we have a motorboat traveling from one shore to the other at a rate of 5 meters per second. Due east encounters a current flowing north at a rate of 3.5 meters per second. Determine the, and then it has questions there, not sure we need that guy. So first of all, let's talk about directional diagrams. I don't know if you guys have done these before, but when we draw a directional diagram, it's nice when we use straight lines, but sometimes we don't. We'll have the iPad help me out. There we go. We generally are going to give this a direction like you would see on a map. So north is usually up, right? South is the bottom. East is to the right, and west is to the left. So this is what our directional graph is going to look like. And we just want to make sense of where we're at with this. So this has a motorboat traveling from one shore to the other at a rate of 5 meters per second due east. So this guy's headed 1, 2, 3, 4, 5, right? He's headed 5 meters per second due east. So he's just headed this direction. And he encounters a current flowing north at a rate of 3.5 meters per second. Okay, so this is the direction the boat wants to move. And he gets pushed by a current that's flowing north, so it's headed north direction, or up at a rate of 3.5 meters per second. So 1, 2, 3, 4. So he's getting pushed to 3.5 there. Oops. Does that make sense? And I'm going to label this 3.5, and I'm going to put meters per second just to help me remember what that stands for. So you'll notice if we're calculating his actual speed, and we won't talk about direction on here, But if we're calculating actual speed, we want to know the length of this vector right here. So essentially what we're saying is, well, we could create a complex number. This number right here that I'm highlighting there, huge black circle, it went to the right 5 in the real direction, so we could say that this would be 5 plus, because it's going up, 3.5 in the imaginary axis direction. So this would be a complex number that could represent that large black point. So if we want to know the speed of the motorboat or the actual length of that segment, then we would calculate the modulus. So again, the modulus of this complex number would be equal to the square root of the first component plus the second component. And we could calculate this. Now again, if you're asked to approximate, then you would go ahead and do so. And in general, it's very common for an approximation to be made on an application problem. So whether you're asked to approximate or not, I'm going to go ahead and approximate just so I can understand more clearly what the speed is going to mean here. So if you plug that into your calculator, 5 squared plus 3.5 squared, and then take the square root of that, we should end up with about 6.1 meters per second. So notice he's flowing to the east, but the current is pushing him, and he's going to be actually going a little bit faster than 5 meters per second because the current is aiding him in moving.